In this lesson, we're going to cover Unit 7, Acquisition 2 on Beer's Law. So first, we're going to explain what Beer's Law or Beer-Lambert's Law is, and then we'll get into some calculations.
So let's say we had 3 test tubes.
This is test tube 1,
test tube 2, and then let's say we had a big test tube. Test tube 3.
So we're going to make a few assumptions. Pretend my drawings looked a little better.
Test tube 1 and 2 are the same width. And then we are going to assume that test tube 2 and 3 are the same concentration.
I'm going to depict concentration just with some lines.
So if we have a solution that is like not super concentrated, it's going to be
light in color.
If I have a solution that is much more concentrated, it's going to be a lot darker in color. So let's say we had a blue solution, maybe it's copper sulfate.
So again, we are assuming 1 and 2 are the same width, 2 and 3 are the same concentration.
So let's say an equal intensity of light. If an equal intensity of light is shined on each test tube,
what do you think is going to happen? Let's compare test tube 1 and 2.
So we shine an equal intensity of light through each of these test tubes.
Which one is going to absorb more light and which one is going to transmit more light? Test tube 2
will absorb more light.
Absorb means that it's going to take in. The reason it will absorb more light is because it is more concentrated. Because it's more concentrated, it's going to absorb more light. There are going to be more particles that can trap that light in. Less light is going to pass through because it's more concentrated. So when comparing test tubes of equal width, whichever solution is more concentrated is going to absorb more light. Well, what if we have the same concentration? Which one do you think is going to absorb more light between 2 and 3? They have the same concentration, but now the width is different.
And our answer would be test tube 3. Test tube 3 will absorb more light
because light has a farther distance to travel. So since that width is greater, it has a farther distance to travel, so more of that light can get trapped in, so more of it is going to be absorbed. So I've been talking about two terms. Let's define them. we've been talking about absorbance. Absorbance is the amount of light that gets absorbed, or the amount of light that cannot pass through a solution. So test tube 3 would absorb the most light. It is the most concentrated and it has the farthest distance to travel. Then comparing 1 and 2, test tube 2 would absorb more light because it's more concentrated. Test tube 1 would absorb the least amount of light. Another term that I mentioned was transmitting. It's transmitting a certain amount of light. Transmittance is the amount of light that passes through. So transmittance and absorbance are opposites of each other. Absorbance is how much light it absorbs. Transmittance is how much light passes through. They have an indirect relationship. The more light that gets absorbed, the less light that gets transmitted. They are inversely related. The more light that passes through, the less that gets absorbed. Inversely related. So this brings us to our Beer's law equation. And we'll kind of put all of this together. A is equal to epsilon LC, where A is the absorbance, epsilon is something called the absorption coefficient. This is going to be the slope of our line. L is going to stand for the length in which the light is going to travel. It's going to be 1 centimeter. And C is the concentration. So we can see that the absorbance, the amount of light absorbed, is going to depend on how far the light has to travel and what the concentration is. For our purposes, we are going to assume that the length is going to be 1 centimeter. All right, let's look at some data and we'll do a calculation. A solution of KMNO4 has an absorbance of 0.539. Absorbance does not have a unit. Determine its concentration. And then let's say we had a data table
So we have a few solutions in which we know their concentration. And we can run them through a machine called a spectrophotometer where it shines light through our sample. And we can get a reading which tells us how much light is being absorbed. And again, no units for absorbance. Alright, so if we were doing this in a lab, we would have 5 solutions with a known concentration. We can run them through a spectrophotometer and record the absorbances. Then we have an unknown solution, and we can put that unknown solution again through our spectrophotometer. The light will shine through it and we get a reading of how much light is being absorbed. We should be able to use this data to work backwards and figure out the concentration. First thing that I want to point out is you should be able to make a very good estimate of what the concentration might be using your data. So take a look at our data and notice that as the concentration increases, the absorbance increases as well, which we would expect. We saw that with the test tubes that we drew at the start of class. So we're going to have a linear relationship. As concentration increases, absorbance increases as well. My unknown has an absorbance of 0.539, which falls between these two numbers. That means that we can make a pretty good guess that our concentration is also going to fall between these two numbers. So I'm going to guess that our concentration is going to be somewhere between 0.09 and 0.12. So this is going to be linear. And looking at our equation, it doesn't really look like it, but we can think of this as a y equals mx plus b. So we know that the length is going to be 1, we're going to ignore it. This is going to be my slope, and then I don't have my y-intercept, but I do know that it is going to go through the origin, so my y-intercept would be 0. If my solution has a concentration of 0, it's not going to absorb any light. So we're going to think of it like a normal slope of the line, y equals mx plus b. And the first thing that we are going to do is determine the slope. The way that we are going to determine slope is rise over run. Change in y over change in x. Again, think of this like the slope of the line. Y is equal to mx plus b. So y is my absorbance. So let's do the change in absorbance. I'm going to pick these 2 points because that is going to be the closest points to my unknown if we were to graph this. So my change in y all over change in x. X is going to be concentration. And then let's solve for our slope. Oh, I dropped a 0. My concentration is 0.09. Oops. and I am getting a slope of 5.7. So again, rise over run, or we can think of it as change in absorbance all over my change in concentration. Step 2, we're going to use our Beer's law equation to solve for concentration. The absorbance of the unknown is 0.539. My epsilon is the slope, which I got 5.7. We're always going to assume that length is 1 times my concentration, and now I can solve for concentration. Zero 0.094561, etc. Let's think about significant figures. Let's look at all of our measurements. Leading zeros are not significant. So all of my concentrations have 3 significant figures. All of my absorbances have 3 significant figures. Let's round my answer to 3 significant figures. 0.0946 molar. Next, we want to think, does my answer make sense? Remember that we said our concentration should fall somewhere between 0.09 and 0.12. I got 0.094. Again, you can think about, does my answer make sense? Well, my absorbance is 0.54, which is much closer to 0.49 than it is to 0.67. So your answer should be closer to 0.09 than it is to 0.12, which again, it is. All right, I know this has been a long lesson, but I want to give you guys more than one example. So let's do one more really quick. So again, we have some data. Let's say we have some solutions with a known concentration, and we run it through the spectrophotometer, and we take absorbance readings of each of those samples. And then we also have an unknown solution that we are going to compare it to. And we want to determine the concentration of the unknown. So the first thing that I am going to do is I am going to predict where my concentration might fall. So an absorbance of 0.446 falls between these two absorbance readings. So I'm going to suspect that my concentration will fall somewhere between 0.3 and 0.4. So the first thing I want to do is determine the slope, rise over run. I'm going to take the change in y over the change in x, or we can think of this like the change in absorbance all over the change in concentration. So change in absorbance, 0.550 minus 0.410 all over change in concentration. We can plug that into our calculator, see what we get. And I got an answer of 1.4. That's going to be my slope. Now I can plug it into the Beer's law equation. Absorbance is going to be equal to the slope times the length times the concentration. My unknown has an absorbance of 0.446. My slope was 1.4. We're assuming the length is traveling 1 centimeter. And then we are going to solve for C, which is our concentration. And I got 0.318 as my concentration. Let's talk about significant figures. All of my concentrations have 2 significant figures. My absorbances have 3. We're going to round to the least number of significant figures, which is 2. So 0.32. Units for concentration are molar. So 0.32 molar solution. Last thing we want to do is think about, does my answer make sense? Does it fall somewhere between 0.3 and 0.4? And it does.